Yep. Okay, we're on. We shall be talking about clustering today. So this is the second week of unsupervised learning. I think it's a very neat topic. So the motivating comic here is simply data can be presented as in groups where there's a lot of ways where we want to find meaningful groups. And of course, the underlying message of this picture is that for a suitably chosen set of groups, in this case, the weight of ourselves, our pets and livestock versus wild animals, we can see that the Earth is in trouble unless we do something about it. I would say that clustering is usually introduced as so the first approach for unsupervised learning for a reason. It's very intuitive and it's widely used. It is, I would say, a fairly non-trivial problem, especially the evaluation of it is non-trivial, but there are many neat algorithms that are associated with clustering that are used actually elsewhere quite a lot. So today we're going to talk about three main things. Basically, what is clustering? And we look at it as from a density approximation point of view. And then what is k-means clustering? Basically, assigning points in, say, Euclidean space to a number of distinct groups. And then what is Gaussian mixture models, inspired, or the methods of which might be inspired to what we have learned in k-means clustering. So it's an ambitious agenda. And hopefully by the end of it, you will enjoy this section. And the brief update is there is no workshop Friday this week. What am I writing? And then clustering and EM lecture number 2 will be after the break. In terms of deliverables, assignment 1 is due today. And I suspect that's the reason why many people are not here. Nonetheless, so the underlying skills and representations that you will gain from this part is an appreciation of discrete latent variables. Last week we were talking about PCA, and that's continuous latent variables. And this week we're going to talk about discrete latent variables. And then, moreover, we're going to gain appreciation of this important algorithm, expectation maximization. This is one of the tutor's favorite algorithm. And so that's enough reason for you to believe that it's interesting. It's a general technique to finding maximum likelihood estimators in latent variable models. This is very powerful and useful. You'll see resemblance of it in graphical models. We don't get to talk about variational inference, but the spirit of that, especially what we cover after the break, will be used in variational inference as well. Or informally, how to solve hard-looking problems by solving several easy-looking pieces, or by first breaking it down and then solving several easy-looking pieces. So let's get started. Is this an old version of? I believe so. Oops. Okay, that's all right. So we have been looking at Gaussian distributions quite a lot, and you might think, oh, these bell curves are kind of boring, right? So they are either fat or skinny or peaky, but what's more to them? So the density estimation version that motivates clustering is, we can actually use these boring looking bell curves to build increasingly powerful and expressive densities, such as this particular one. I believe it's invented from the teams teaching this class in previous years, and it has a distinct Australian spin. So we can make a density look like a wallaby. In case you're new to Australia and don't know what wallaby is, the picture is on the right. Basically, it's a animal macropods family, or of the marsupial class, basically animal with bags, that looks like a kangaroo but is quite a lot smaller, right? So you can see that, well, we have the wallaby tail as a peaky part, and then there is a gentle bump, and then there's a wide spread. So how do we make a distribution like this? The answer is by superimposing or composing several simple bell curves. In this case, there are 3 bell curves. The first bell curve with the mean at 5 and variance at 0.5, so it's the peaky one, this one. The second bell curve with the mean at 9 here, with a larger spread, slightly larger spread, is this one. The third bell curve is with the mean at 2, which is around here, and then a large spread with variance at 20 is this background, or what color is it in this other plot? Anyway, so you can see this here. And it's a weighted sum of 3 Gaussian distributions, right? Slightly more formally, any smooth density function, however many modes that you have, whatever shape it has, can be approximated to arbitrary precision by a Gaussian mixture model with enough components. In this particular one, by eyeballing, we can see maybe 2 and 3 components suffice. You can imagine this getting quite a lot more complex if your modeling needs arise. So that's a reason when we should care about Gaussian mixture models. And there are theoretical results about this documented in papers and books in the last 25 years or so. So that's cool. That's neat. So before we talk about basically composing Gaussian components to make mixture models, here is its simpler relative. It is simpler in a sense is we can, what the goal of this, or the goal of clustering in general, is to partition the data into a number of clusters, where the number of clusters k is given, right? You look at, well, in simple cases, we can simply eyeball the data and say, hey, the data look like these green dots, and it looks like there might be 2 or 3 groups. Maybe there's a group in the middle or something. I'm just gonna try 2 for now, right? And the intuition of finding the groups is that we want to prescribe that, well, each cluster contains points close to each other. That's the meaning of clusters. And we will want to introduce a prototype for each cluster so that, like, we assign, let's say the prototype intuitively should be here and here. We assign each point in the space to the prototype, and then the assignment should incur some notion of minimum loss, right? So the k-means algorithm, it is important in basically this representational simplicity. It is also important, as we will see, as inspirations for more general algorithms. It's also known as vector quantization in engineering, especially electrical engineering. And then the algorithm that allows us to perform k-means is also known as Floyd. Okay, I'm not gonna be, okay. I'm not sure what the exact name is. So I'm gonna wipe this to prevent myself I'm saying something wrong. Go away. So the point I was trying to make is the k-means algorithm are known by different names, as we said about PCA, right? So the k-means, you can think about it as a discrete latent variable version of PCA. It's also important. It has different names in different fields, and it's quite widely used. Despite there is an abundance of clustering algorithm in recent years, this is, again, still one of the robust and simple baselines that you would actually try on any new data set, along with all the fancy clustering and like latent variable inference algorithms that you might want to try. So the algorithm proceeds as follows. If we assume that we have some prototype, right? It can be arbitrarily assigned at the beginning, such as the red point here and the blue point here. We could say that, hey, we want to define a loss function. And the loss function can be that basically it's the distance or L2 distance, Euclidean distance, between the data point and its corresponding prototype. Then how do we denote that we're assigning, let's say, a point to its corresponding prototype? It is through this binary indicator assignment variable that uses one of k encoding scheme. So basically, R of n is a vector of assignments. It could be like 0, 1, and then zeros. So basically, this says data point, the assignment vector for data point xn is this vector, and then it is 1 for the cluster that it's assigned to, 0 everywhere else, and one of k encoding scheme, as we have seen repeatedly in this class. So if we use that assignment scheme, we can see that for a given data point, so only one of k terms is non-zero, right? And then the rest of it is 0 because the corresponding R and K is 0. So our distortion measure here is simply the square loss between the data point and its corresponding prototype, written out with this assignment binary indicator variable. So the k-means problem here is essentially we want to find values of the assignment variable and the mean vectors. Basically, we want to better position the mean vectors in the blue cross and the red, denoted by the blue cross and the red cross here, so that intuitively speaking, we can imagine that if we move the red cross to the middle of the data point here and move the blue cross to the middle of the data point here, we will have lower loss, right? Right, from this loss function, we can see that the x are given data points. There are two unknowns, r and k and mu k, that determines the value of the loss function. And it also completely determines the intuition of the k-mean clustering that we want start out trying to solve. Basically, what are the prototypes and how to assign points to clusters. The bad news, however, is that, well, this j function is quadratic in mu of k. So that's good, but then it's multiplied by r and k. So it's not like one of the nice loss functions that we're used to, right? So neither linear nor quadratic. Moreover, this r and k is discrete. We can't really differentiate with respect to r and k, right? Technically speaking. So how do we resolve this? Divide and conquer it is. So this is how, like, me as an engineer like to think about problems. So if we stare at this j function again, we can see that, well, technically speaking, if we had the prototype centers, we can assign points to the centers. If we have points that have existing assignment variables, then J becomes like a square loss, and we know how to solve that. So right for now, we are just going to pretend that, say, mu sub k are given. Let's say these 2 points on the plot. It's not particularly good, but let's say we run with it. Then we only need to determine the assignment variables R and K. Right. So in order to minimize R and K, or minimize J, and we have freedom to vary the assignment variable. So what is a good scheme, right? So for, let's say, like if mu k fixed, right? For a set of fixed mu k, we essentially have, say, we can compute the distance between any data point xn to mu1. Take the 2 norm, xn to mu2. And if we have more than 2 points, xn to mu bk, right? We can see that we have already constrained R and K to be binary or one of K encoding. We can just take this whole vector and pick the minimum entry. That will essentially minimize the sum, like within the nth data point upstairs. Right, so this is exactly what the expression here in 9.2 says. So basically take the minimum out of these potential assignments, and then make that corresponding R and K 1, the other ones 0. So intuitively, you can also see that with mu k fixed, this assignment scheme minimizes the loss function J with respect to R and K. Right. Cool. So we just said that these 2 sets of variables sort of depend on each other. Now we have a solution with one fixed. How about mu k then, right? The top part of this slide is the same. Now our focus is mu k. Assume R and K is null. Assume we know which data point is assigned to be. Let's say data points over here is assigned to this, and the rest are assigned to the red center. If we know how to differentiate with like a norm function by now, so we just do that for equation 9.1. We end up with this expression. We stare at it and we said, oh, right, that's easy. We just move the terms involving UK to mu k to the other side, and then we get this. So this expression is basically the sum over n on either side is still there. Basically is on the top is the average, or it's the sum of the data point coordinates divided by the number of data points assigned to cluster K, right? So this is number of xn's assigned to cluster K. And the same term appears upstairs. So basically, it's just if we would like to update mu k, we're just going to look through the points that are assigned to this blue center, and then we compute the average as the new mu k. That will visually put us somewhere here, right? Because there's more data. The data is denser here. So that's the update rule of mu k, right? Mu k moves from there upstairs to downstairs. And that visually also looks reasonable because now in one step we have already moved mu k to where the points are. So just a recap to the two steps we just talked about. It says, well, what is called the expectation step here is basically reassign data points to clusters with a fixed cluster center, and that determines R and K right here. And in what's called maximization step, don't mind the names so far of, well, for now, it will be clear after we talk about like the different views of EM algorithm after the break. In the maximization step, we recompute the cluster means by fixing R and K and updating mu, right? And we keep doing this until what, right? So there are a number of things that we should ask before we make this a complete algorithm, right? So in terms of where to start, we can say we can randomly put a starting point, or say randomly choose data points as the starting point, pick k out of x n data points. So the idea is that if we randomly pick any data point, they could be, as indicated in the last version, arbitrarily far away from the actual data point. And that's not an ideal start, right? So you can also imagine that one partition of the data that these two centers could have could be like cutting this lengthwise, and that's not optimal, right? And in the next workshop / lecture, we can also talk about like a very recent, recently proposed principal method for initializing k-means called k-means plus. That's not in the textbook because it was invented right after the textbook is written, but it's very clear. So for now, we just say we just randomly pick some data points. And then you may also ask when to stop, right? If we stare at these two steps, we can say that we can decide to stop after either the E step or the M step. Right, so we just write it out. For the E step, expectation step, we can stop if R and K did not change or does not change after the If the cluster assignment does not change, we can see that with the maximization step, the xn's are fixed. If the R and K don't change, then mu k's will not change either, right? Yeah, for the M step, we can stop if the set of cluster centers do not change, or basically the sum over k, the change of the cluster centers over different rounds. Okay, it's too long. Is less than some epsilon. We already said that the first stopping criteria, if satisfied, implies the second. If there is absolutely no change of the mu case, it also implies that the RN case won't change, because if the cluster centers don't move, then the assignment also won't move. In practice, if especially when we have lots of data, the cluster assignment or the cluster centers might move by a epsilon, by a little bit. If the epsilon is small enough, then we kind of can declare that the algorithm has converged. In practice, we can also say, or maximum iteration reached, then we stop. It doesn't mean that the algorithm has converged, but we just run out of patience. So these are stopping criteria. And we might ask, we just intuitively sketched out these two steps. You may ask, why do they work? Right? In terms of the k-means algorithm, these two steps work. Well, in a way, we can say that while fixed mu k, then we minimize the loss function j. With respect to R and k, we get the E step. And if we fix R and k, we minimize the loss function. We know that the mean minimizes this here, the mean of the data points minimizes the square loss function, so that works. But we're actually somewhat cheating here, because we're minimizing j with respect to two different sets of variables. This is nice in a way. It's you can think of it as, for example, j can have like let's say the landscape of j may look like this, where this is some r, this is some mu, and what we're doing is essentially moving coordinate-wise, right? Rather than doing gradient descent, joining in the two space, we're now moving coordinate-wise. First move along r, then move along mu, right? Exactly why this is optimal will be covered in the next workshop. But for now, you can see that there is some intuitive reason why this is a good idea. All right, here's the graphical example, right? It wouldn't be satisfying if we don't see k-means algorithm at work at this particular toy data set. It's actually the what's called rescaled Old Faithful data set. So Old Faithful is a hot spring in Yellowstone National Park in the US. It intuitively has two modes of eruption, right? So I believe which is the interval between eruptions and the time the eruption lasts. So it has a small mode where both is small, and it has a large mode where you wait a long time, but then it spurts out lots of hot water. It's a tourist attraction. I've been there, and it's quite photogenic as well. As we stare at this initial, assignment of the clusters, indeed, the initial assignment of cluster partitioned the data set lengthwise, which is the opposite of what we wanted. But even that, it allowed the two respective clusters to move closer to the data points. Because they are slightly off-centered and the data point is dense on one end, we can see that, there is more of blue points in the lower cluster, and there's more red points in the upper cluster. And then if we run this again, so if we run the assignment algorithm for the two updated centers, we get most of the blue points in the lower part assigned to the updated to the blue cluster again, and the red takes care of the upper cluster. And here is the essentially separating boundary between the two clusters. Right. This is neat. With two, actually with two or more centers, the separating boundary of k-means on the Euclidean space is always a straight line. Why is this the case? I leave you to think about it based on what we learned so far in this semester, right? So what do classification or what do discrimination boundaries look like? And what's the underlying connection to high-dimensional Gaussians? So then we do this one more time. Giving the assignment out, having updated R and K, now we update the cluster centers again. Now you can see that the cluster center moved to the dense area of the points, and it induces a new separating boundary, right? And you do this a few times more until it converges, where the boundary don't move between, let's say, this picture F and the H. It moved by a little bit, and the centers don't move again. So what do the cost function look like? The cost function J, involving both R and K and mu K, is plotted here. And the number of iterations, here number of iterations refers to one E step and one M step combined. Therefore, there are essentially two colored points in this plot, right? So you run the initial E step, the initial loss is here, and you run the M step, the loss drops, and then E step again, and M step again. After 4 iterations, it pretty much converged. So that's nice. It's sort of illustration that k-means really works. In fact, right, k-mean is designed to find sort of ball-like cluster in high-dimensional space. And if you can visualize the data in the original space, it often looks quite nice. So that's good. We covered initial conditions and a lot of other things. So the initial condition is quite crucial for convergence. There can be arbitrarily bad initial conditions, right? You may say there are a number of pathological conditions. So in this EM or iteration, vector quantization iterations, it finds a local minimum of the loss function J. In other words, as we saw, J is not a linear quadratic function, but generally in R and mu, we don't know what the global loss landscape is like, right? So another thing is a practical consideration is what to do with empty clusters, right? And by empty clusters is what we mean by what if R and K, there is a K where R and K for all n. Okay, it's better to write it. For all values of n, all 0. Meaning if no data point is assigned to a cluster center, then what do we do, right? Does the cluster center die? Right. If we proceed with this, we will not have a valid mu k to update. Why? We can't update mu k. What to do, right? So we can declare that no, like we just have one less cluster center. That brings us back to the question of how many cluster centers should be there in the first place. Or we can basically reinitialize mu k to another data point, right? In that case, there is at least one data point assigned to mu k, the one that it's sitting on, and the cluster won't die, and it will correctly return k clusters as asked. So that's the preferred approach. So you can also ask, because it's a machine learning class, not a statistics class, we can ask we care about how long this takes. So the computational complexity is, well, computing J, as we saw earlier, is sort of proportional to the number of data points, proportional to the number of cluster centers, and also proportional to the data dimension. So it's sort of a linear algorithm overall, but if these factors can sort of add up, right? So in certain cases, right, this can get really expensive, finding the nearest neighbor. So in the step of assigning, like find R and Ks, we wanted to find basically nearest mu for each xn, right, for all. And this can be expensive if we have lots of data points and lots of data centers, right? Data points, say, in the order of millions or billions, and cluster centers in the order of 10,000s. Then it might take too long on a single machine. In that case, we can use triangular equality to rule out some of the mu's, and we can use, for example, tree structure in high-dimensional space to, again, rule out a lot of the mu's before we need to compute. Like, we don't need to compute all pairwise distances between the centers and the data points. So that's sort of a computational issues in a nutshell. We're not going to go into detail here. It will be relevant if you use k-means in large data sets. In the scope of this class, we are not going to be able to go on this because all the homeworks, assignments, and exams are not going to require that much computation. Otherwise, you won't finish or take you too much time. So the next set of comment basically says we can derive stochastic versions of the k-means algorithm to make it faster or slightly easier to run on with large data sets. And the k-means algorithm also generalizes to non-Euclidean dissimilarity measures, such as if we say, oh, what if we don't want square laws? We want what's called median. We want the cluster center to be the median of the data points, and that's possible. So this is called the K-Medowitz algorithm, where we define this function nu as not a square laws, but something more general. So how is K-means algorithm used? So this is the picture from the book. The intuition of these pictures is that an image is represented, right? So an image pixel is represented by a RGB tuple. And because of the sensitivity of the human visual system is only about, like the sensitivity is about 5% of the dynamic range of light in each of the RGB channels. So traditionally, each channel is encoded with an 8-bit integer for each channel. And the value of that is from 0 to 255. Or if we speak in hex, so that's 0 to FF, 0x, so to speak, right? So if each pixel is 3 8-bit integers, so that means it's 24 bits per pixel. And how many different values is that? Is actually quite a lot. I don't have the number in my head, 64K or something like that. So if we think, right, 24 bits per pixel is quite a lot, can we ask k-means to help us reduce that? Well, this is intuitively the notion of finding groups in data. If we have less groups than the number of possible values in data, then we essentially have a better or more parsimonious representation, right? So if we cluster this original image into two clusters, then it basically finds the lighter part of the image versus the darker part, including the child's hair and including most of his skin as well, because of the lighting, right? In here, the light shines from here, and this part of skin is brighter, and this part is darker. So that's not very good. And it, so going from 24 bits to essentially just two clusters makes this image looks quite horrible. But what if we just increase the number of clusters to 3? Then we can already, it looks like a comic picture, but it allows us to discern key features and key objects and shapes of the image already. So we can see the kid's face. There's a light, medium, and dark part of the image, so that's pretty good. Even if we represent the whole color space with k equals to 10 clusters, it has a lot more detail, right? It even has this cartoon character at the back clearly visible. So, right. So from like 24 bits, which is 16K, 16 times 1024 colors, to 10 different colors, there's lots of savings already. Again, as we said in the last week, this is not the best algorithm, by far not the best algorithm for compressing images, because it doesn't make use of the fact that neighboring pixels tend to be the same color here. But as you can see, it's doing a pretty good job. There's visible distortions of the resulting image, but it's sort of, you can decipher a lot of the image content already. It also claims to segment an image into regions of reasonably homogeneous appearance. It's homogeneous in terms of color. It is not homogeneous in terms of shape, as we can see that there can be like singular, like individual pixels that get assigned to different cluster than its neighbors, right? So it says this is done by running k-means on all pixels until convergence, replace all pixels with the corresponding mean. This example is also useful to illustrate that the mean lives in the same space as the original data point. Thereby, like if we replace it with the mean, it's still a valid color. You can still see an image. So this is resulting in an image with a palette of only, say, 10 different colors here. There is better approaches to both image compression and segmentation, but this is just an illustration. If we were going to store the image compressed, we just need to store the mean vector, and also where each, we also store the data in the form of the reference labels, basically this 1 of k encoding. The new data points, if we have a new image, which is, let's say, a different picture of the same kid at the same scene, but from a slightly different angle, we can just map the new picture onto the set of codebook vectors by finding which one is closest in color. This technique is also called vector quantization. If I believe most of you have used the quantization feature in the programming language, right? If we say quantization of x up to, say, the level 10, then like essentially we say how many significant digits we want to keep of x. In here, it actually solves the question of if we have a vector x rather than a number x, how do we quantize it, right? We can go around by just quantizing each dimension separately, but that's not optimal. In here, we're doing the quantization with the criteria of minimizing the Euclidean distance. with respect to each dimension, as we can see that if we were doing quantization of the original space with each dimension done separately, then it's basically we'll quantize, let's say, this space into 4 pieces. But this piece is mostly empty. This piece is mostly empty, right? Then this is not the best use of our quantization codebook. But if we were doing it with k-means, it's an adaptive vector quantization that zooms into the dense areas of the data point, and that's conceptually better. So that's the story about vector quantization. So we're pretty much done talking about k-means, and it's about half the lecture. Let me pause to see if there's any questions. No, people are happy. K-means is easy to understand, right? So now let's move on and look at the wallaby distribution that we looked at earlier. So hey, here x is in 1 dimension, so it's somewhat different than k-means. But as we know that we like to go look at Gaussian mixture models in 2D as well. So some of the intuition will soon come back. So more formally, we're looking at mixture models in general, right? And in the rest of this workshop, we're going to look at Gaussian mixture models, basically a mixture of Gaussian distributions. So first of all, mixture distributions are formed by taking linear combinations of more basic distributions. In other words, it's exactly what the wallaby distribution looks like. It's P of x, the marginal distribution over x, is a linear combination of Gaussian distributions down here, where the weights are denoted by a set of real numbers, pi of k, where they live on the simplex, or in other words, each of the pi of k is greater or equal to 0, and they sum to 1. So the book, the mixture distribution is introduced in chapter 2 of the book, but Gaussian mixture models and k-means are in chapter 9 of the book. So it's a bit of if you need to flip back a little to essentially know the whole story. In chapter 2, it basically said what we said in the beginning. If we use a sufficient number of Gaussians, and if we can adjust their means variances as well as the coefficients in the linear combination, almost any continuous density can be approximated to arbitrary accuracy. So you can make this statement more precise by defining how you define arbitrary accuracy and so on, but this is the spirit, right? And the reason we care about Gaussian mixture models primarily is also because, hey, by just using Gaussians, we can approximate any density already. There are many other elementary distributions with the same property. We're not going to go into that. And we care about Gaussians because, hey, it's quadratic. The PDF function is, the log of PDF function is quadratic, and that's nice. We like to work with it. All right, so here is a picture of Gaussian mixtures in 2D, right? So this is one step up from wallaby distribution. Let's call it the the realistic landscape, right? We know that each Gaussian distribution corresponds to an ellipsoid-shaped mountain in 2D, right? And if we just basically overlap 3 mountains and make them overlap in spatial extent, then we get essentially this complicated looking contour in 2D. In 3D, well, if we really draw the mountain, we can see, oh, this looks like well, maybe the Australian Alps, where there's one hill after the other hill and so on, and mountains around the world. One view that will help us model the Gaussian mixture model is so-called latent variable model. So in this class, we haven't formally introduced latent variable yet. It's actually in chapter 8, I believe, in the graphical model chapter that comes before this chapter in the book. But I thought, given that we're talking about GMMs first, it's also a gentle introduction about what latent variables mean and what graphical notations mean. So again, we have X, that the marginal distribution of which it can be rather complicated. It can look like this, let's say. And now we have Z. Z is, let's say, it looks like the one of K encoding discrete variable that we're familiar with. Again, the distribution of X is a weighted sum of Gaussians. There's some pi K, which are the weights. We connect the Z variable, the latent unobserved Z variable, to pi Ks. Basically, the probability of each component in Z being activated is the same as the mixing weights of the marginal distribution of each of the Gaussian component, right? And the marginal distribution of the latent variable. So when we observe data point, we only observe this wallaby distribution, right? We don't observe exactly which the value of Z. That's why it's called latent. Okay, this is latent, unobserved, and X is observed. Right, and we can trivially write out the joint distribution of the latent variable as essentially a product of these pi's raised to the power of Z, right? So Z is 0, 1, and this is basically, as we have also seen with one of K encoded binary variables, this basically says P of Z equals to pi of K for that particular mixture mode or mixture component that's active, and it's actually 1 everywhere else. When it multiplies, the ones get ignored, right? So again, using our familiar pattern of specifying the model before we talk about its inference and learning. So here is more, here are basically derivatives of what the model specification is. In the last slide, we talked about the model specification in terms of the marginals, P of X and P of Z, and what Z is, how Z is defined. We haven't talked about this arrow in the middle, right? How X and Z depend on each other. And the next slide actually talks about that. Right, so it's basically, what does this mean? It says, well, given that we've already specified Z, P of ZK equal to 1 is pi K, right? We now want to use Z to help simplify the distribution of X. And the way to do that is to say that condition on a particular ZK, the ZK already sort of implicitly encodes which mixture component it is, then X is just a simple multivariate Gaussian distribution. So X is Gaussian informally conditioned on Z. Written in vector form, the vector of X conditioned on the vector of Z is, again, the product of Gaussian distributions, except only one of these is active. And what does this allow us to do if we specify the dependence between x and z? Now we wanted to check whether this specification preserves some of the basic model assumptions we had, which is the mixture distribution of px. So if we use Bayes' rule or the sum rule of conditional probabilities to basically say, well, we use this simpler form of P of x given z, multiply by P of z, and sum over z. What do we get, right? So the terms inside is essentially pi k of raised to the power of zk, and then normal distribution raised to the power of zk. Taking the product over k and summed over z, right, as a vector. So making use of the fact that only one of the k's, if we sum over all configuration of z, we can see that it goes back to the mixture form that we initially assumed. So that's encouraging. So we just used Bayes' rule and did a linear combination of Gaussians. No big deal. We haven't used Bayes' rule in the other direction, right? So we looked at, we said, well, for x and z, we looked at P of x given z. We haven't looked at P of z given x. Now let's do that. So let's define a responsibility variable called gamma z of k. Basically, it's defined as probability of z of k, the z k's component of z being 1 given x. And we do so by essentially using the Bayes rule as that being P of x and z over P of x, right? That k equals to 1, right? So let me write it out fully, maybe more precisely. Right, P of x, as we saw, was the sum of a mixture of Gaussians, right? The mixing weights is P of probability of z equals to 1 over all components times the Gaussian distribution. And the joint probability of x and z equals zk equal to 1 is that particular Gaussian component, right? So what this translates to is the responsibility vector is the weight, the corresponding Gaussian component times its mixing weight over P of x, or the sum over all of such terms over all k. It also makes sense in, so the way to intuitively make sense out of this is to look at, let's say if we have two Gaussian components, one look like this, the other one look like this. And if we're interested in gamma zk, as we can see, this function is a function of x. It depends on x, right? So if x changes, so well, graphically what this means is like, let's say if we term this part pi 1, n of x given mu 1 sigma 1. And then the other part, this part, being pi 2, and this Gaussian likelihood of x mu 2, sigma 2. Then the responsibility from the red component is essentially the height of this red component divided by the sum of the red and the yellow component together. And this is quite intuitive, right? So as we can see, towards this end, right, the gamma of x2, the responsibility for the yellow component, is close to 1. And gamma of x1 is close to 0. And vice versa, on the left-hand side, the responsibility of the red component will tend to 1. And then in the middle, there's a mix. And how the magnitude of the mix depends on the ratio of the two conditionals. So I hope that's intuitive. So here's the illustration of this responsibility variable. For the 3 mountains example we saw a few slides ago. Here are 3 conditional Gaussians, red, green, and blue. Here is the mixture. Well, if we sample from the full mixture, we get this. Right. There are a total of 500 points. And then if we color each point in the RGB channel based on the responsibility of each of the mixture components, we can see that in this area, it's far away from the blue and green component, therefore it's mostly red. Same here, it's mostly blue. For the overlapping region, however, in this region, for example, it's roughly a mix of green and red, right? When it's more towards the center of the red component, these points are more red and less green, and then more towards the green and blue component, these points are like close to black or dark gray because it has contribution from both the red, green, and blue component. Right. So that's pretty neat. So why are we talking about the posterior? It's sort of a sort of a complicated mixing expression, right? And the reason we're talking about it has remote resemblances to the k-means responsibility variable. So what does it mean to do maximum likelihood estimation of the Gaussian mixture of Gaussians, GMM model? So in here, as we said, we observe a bunch of X drawn from the mixture, let's say like these. We observe the purple points. We don't know which one come from which color. And we assume we know the number of components that consist of this. Let's say 3. Someone told us 3. We don't observe which point came from which component. We would like to estimate the mixing weights pi, as well as the mu and sigma of each component. Right. So in this, we now essentially augment the little graphical model with a bit more notation. What it says is still there are n different points, big N different points, each of them denoted by x sub n. When a variable is observed, it's shaded. This is like the convention of graphical models. When there are n copies of it, there is a plate or a square around the variable being copied. So for each xn, there is an unobserved or clear node z of n as a vector. Outside of this copying notation, all of these n data points share the parameters pi that governs the variable z. and mu and sigma that governs x of n condition on that, right? So the arrow of in the graphical model notation denotes dependence, or the like the end of the arrow. The variable at the end of the arrow depend on the variable at the beginning of the arrow. So as we can simply spell out the likelihood, data likelihood here. This part is P of X, right? P of X n. As a mixture model, the log data likelihood is simply taking the log of P of X and then summed over all the data points. The data points are drawn IID from this mixture distribution. Therefore, there is like a summation sign after we take the log. Okay, so what are the possible issues of this data likelihood, right? So besides this data likelihood is more complicated looking than what we're used to, because now we are doing log and then there is a summation sign inside. We were used to like taking log of Gaussians, then we immediately get the quadratic form inside the Gaussian. Now we can't because there is this summation sign in the way. Besides that, there are other complications. One is parameter space symmetries. We've seen this in neural networks. Now we have k different Gaussian components, and none of it is particularly special, right? In terms of, for example, the coloring of these components, we could well call the middle component red, and there's no stopping of that. In other words, if there are k components, they have permutation symmetry. That's what it says. A k component mixture can have a total of k factorial equivalent solutions corresponding to k ways of assigning the k sets of parameters to k solutions. Okay, so that's bad news. There's wave space symmetries. This is also called identifiability problem. Basically, even if we know what the landscape of that complicated looking likelihood function was, it has k factorial global minimums, right? So what this means is at least k factorial global minimums. If we can find them that are equivalent, right? Right. There's also the problem of singularity. We kind of talked about this in k-means, about like what happens if we have an empty cluster. Moreover, in k-means, if there is a cluster with only one point, it's not such a big deal. With Gaussians, as we can see, if we have a bunch of points that are sampled from a Gaussian, then we have only one point. We know that we cannot estimate the variance of the Gaussian from only one point, because there's no notion of spread from the mean that one point will become the mean in maximum likelihood. So that's a problem. So these problems aside, so the solution to essentially the collapsing variance here is to force, numerically enforce that the variance of a Gaussian should be strictly greater than 0. In high dimensions, that means the covariance matrix is non-singular. But these are implementation details, right? So let's first solve the conceptual problem of how to maximize this likelihood function. As we said, it's more complex than for single Gaussian. The summation over different k components are immediately inside the logarithm, and we don't know how to deal with that. And then if we just try setting the derivative of this thing to 0 in a brute force manner, we can see that, well, there is pi of k multiplying this Gaussian thingy in right. So the expression seems awfully complicated. This does not mean that we cannot use gradient-based optimization, right? As we kind of mentioned, the automatic differentiation packages that are in use in the modern days can very well deal with a function like this by essentially breaking it down into the exponential part, the multiplication part, and the log part, and you can well try doing that. And it's not necessarily a bad solution. But for this particular section of the class, we are going to say we want a conceptually interpretable and clean solution, right? So that is the EM algorithm that we're going to spend the rest of this session talking about, essentially. The strategy is, again, divide and conquer, as we have done for k-means. We take this log likelihood function. Again, the divide conquer approach is that, well, the whole optimization, okay, the whole problem, as we said a few slides ago, is we want to solve for pi, mu, and sigma. So maybe let's just look at what we can do for mu first. We take this whole complicated expression, we differentiate with respect to mu. What would that do for us? So we first call this term L, let's say. We differentiate L with respect to mu k and or only one of the means. If we apply chain or familiar chain rule by now, we will get it's a summation over all data points. So the summation is sort of the mu k term inside each sum is the same. So that summation term stays. And if we apply the chain rule, the next thing we encounter is a log. So therefore, the derivative of the log is 1 over the thing being differentiated. So therefore, we just write this big, this giant fraction with the sum term in the bottom. It's xn mu k sigma k. Okay. And what goes, and now we need to differentiate the inside bit of this with respect to mu k. We notice that for this, like only one term is relevant. Okay, let me see. Formally depend on mu of k. So only that term with respect to the small k stays. So pi k is a constant with respect to mu k, so that stays. And if we differentiate this Gaussian function term, we can see that it's basically some constant times exp of some quadratic of mu k, right? So there's, and if we are looking at terms like this, the constant basically carries over, and then the exponential term first, the derivative of x with respect to its exponent is itself, but there's a negative sign in front, so therefore there's a negative sign. And then there is the, let me just loosely speaking, negative of some constant, some exp of mu, quadratic of mu k, and then other things, right? So you can fill out the details after the fact, but basically after this one, you can regroup the terms here, right? So this and then some of the same constant, and these goes to the top here and become essentially the conditional of x given the case component here. And the notation have gotten confusing enough that it's worth renaming the summation variable here k to j. And now we can see that this emerges as the responsibility variable gamma of z and k. The hidden variable z has k components for each data point, therefore it's z and k. And if we remember how the differentiation of quadratic term works, it's basically then comes out as the covariance matrix sigma k, which is constant for this purpose. So it's this bit that comes here. And then the quadratic term becomes a linear term, xn minus mu k. And setting that to 0. Okay, this is still a somewhat complicated expression, but it's less complicated if we regroup it, right? So in here, it's basically setting the derivative to 0 is minus of sum over gamma z and k, sigma, and then xn minus mu k. We can, well, loosely speaking, so if we assume that the sigma is non-singular and it's on both sides, we can multiply this gamma is a number, sigma is the matrix, xn minus mu k is a vector, so we can multiply the inverse of it, loosely speaking. In practice, your sigma's matrix, covariance matrix can be singular, but let's say we don't need to worry about this. And then we move the terms around. It basically becomes something like gamma times mu k equals to gamma times xn on both sides. And more precisely, it boils down to this equation. Basically, n of k is basically the sum of the responsibility values or posteriors over all data points, over all n. So it's number of, it's weighted version of data point, number of data points in cluster or in component k. Right, so this is quite similar to the sum over R and K scenario, binary R and K in K means, right? So, and mu, or the cluster centers, are essentially an average of points inside cluster K divided by the number of effective points in cluster K. So that makes sense. It's intuitive. And in a similar vein, we're essentially going through the same derivation exercise. In that case, if we do differentiate with respect to covariance matrix sigma k, we can see that, well, this quadratic term then becomes the linear coefficients in front of sigma after the log. We essentially have the same expression. So the covariance matrix for a particular component is essentially the empirical covariance weighted by the responsibility variables divided by the, again, number of effective points in cluster K. So that's quite intuitive, and we can sort of intuitively believe that this is a good idea. And also note that this expression 9.17 is quite similar to the corresponding update of means in k-means. You may ask why. We'll cover the full reason why next time, but right now you can make the intuitive connection. So what about pi of k, right? We solved 2 out of the 3 variables we wanted to solve. So these pi of k's, they are simple looking. They're just k numbers. But to solve this, we need to introduce Lagrange multipliers that we covered early on. So we just introduce a Lagrange multiplier because they sum to 1. We just try to maximize, say, log of the data likelihood given all the parameters plus lambda times sum of pi k minus 1. So this term is 0. Adding this Lagrange multiplier term does not affect the value of the objective function. And plus, from the result of Lagrange multipliers, we know that the optimal occurs at the point where this constraint is tight. So that's nice. We do so. Note that the pi k does not appear in this whole Gaussian likelihood term, right? So if we differentiate, the differential with respect to the log will still send the whole mixture probability downstairs as the denominator. On the top, the Gaussian likelihood will just become the multiplier of the pi k term, so that's these terms. And sum over n is as usual. And this lambda term results from differentiating this sum with respect to pi. Therefore, we just have lambda. There's only, like, for each pi k, only one of these terms is active, and the one just vanishes because it's constant. So we have this. And after solving this, and also solving for lambda, which turns out to be minus n, we get this. We get essentially pi k equal to n of k, or in other words, this is sum over gamma, the responsibility vectors, z and k over n. The effective, so pi k is the effective number of data points in cluster k over all the data points. So that's also quite intuitive, right? So for k-means, we don't really have this term. In here, we're just saying scale each of the Gaussians with respect to proportional to the number of data points in it. So we can also intuitively believe that. Okay, so we're done with the main algorithm for Gaussian mixture models. Let's take a step to reflect what just happened. What we did is assume that we have these gamma and k variables. And we use them to solve for pi, mu, and sigma, right? All of these expressions, n of k, depend on the gamma, and then pi k depend on gamma again. So similarly here, both the n of k part and also this gamma part explicitly depend on these posterior responsibilities, right? So given this posterior probability, solve for the 3 parameters. But in here, the posterior probability variables is computed from the pi, mu, and sigmas as illustrated a few slides ago, right? We used Bayes' rule to derive gammas. Now we use these gammas to compute the Gaussian mixture model parameters. So this is, again, a divide and conquer scheme, right? So we call this, in the expectation step, or E step, analogous to k-means, we compute these gammas. In the maximization step, we not only update the means, but we also update the cluster variances and prior probabilities pi, right? So this is graphically what happens. Given the same data set, now we want to model it using Gaussian mixture models and not just k-means. We initialize 2 arbitrary data, well, mu's and sigmas, and here we don't know better, so therefore we set sigma to ball-shaped isotropic Gaussians. In the first iteration, they still this particular assignment still sort of decides to partition the data like lengthwise. But then after we update the mu's and sigmas, we can see that again they move towards where the data point is. And after 5 iterations, we can see that, oh, the lower cluster, the blue cluster is capturing the lower Gaussian, and the red is capturing the upper Gaussian. After 20 iterations, rather than 4, as in the case of k-means, we can see a pretty tight blue cluster downstairs and a pretty tight red cluster up. What's different here is that compared to k-means, each of the cluster not only has a center, but it also has a covariance matrix, which is not circular, right? So the resulting cluster boundary is no longer a line. So this is strictly more general than k-means in the sense that we both will have a weighting between the two clusters. Each of the cluster also has a shape, like i.e. the covariance matrix that can point in specific direction. All right. So as we kind of said, there is a conceptual connection between the responsibility variables or the assignment variables in k-means. We call them hard assignments. Basically, R and K is either 1 or 0. So if Xn like belongs to cluster K, and otherwise, in here, the gamma are just soft responsibilities, where it computes the extent that Xn belongs to each cluster using a principled approach, the posterior probability of the cluster given the data. Right. So in other words, gamma of Z and K is probability of Z and K equals 1 given Xn. Here's a recap of EM algorithm for Gaussian mixtures in general. Again, given a set of data, we initialize. How to initialize is a good topic. And here we can initialize using k-means. Initialize using k-means to initialize mu of k. Covariance, we usually set them to be isotopic. Missing coefficients can be initialized uniformly. And then we evaluate the initial likelihood value of the log likelihood, compute the responsibility or posterior of mixture component given data. And then we use, in the M step, we compute a new set of parameters, mu, sigma, and pi, which relies on this effective number of points in clusters. And then we evaluate the log likelihood. And in here, we check for convergence of either parameters or the log likelihood. So basically, in here, there is an overall function if the parameters don't change or change less than some small epsilon, or the log likelihood change less than some epsilon, then the convergence is reached. In here, because the responsibility parameters or the variables are real valued, it's harder to ascribe that they don't change at all. You can also prescribe them to be changing less than epsilon, but the core or the goal of Gaussian mixture model estimation is optimizing the likelihood. So checking for this is direct. And also the parameters of the Gaussian mixture model are these. Checking for convergence on these are direct, whereas the responsibilities are just intermediate variables. So that's all we needed to say today. We talked about mixture models. Why do we care about clustering? It's conceptually attractive, and it's discrete latent variable models. We talked about k-means and Gaussian mixture models. We talked about expectation maximization algorithm across the two. In the next workshop after the break, we're going to talk about like why is it called expectation and maximization. And we also will talk about why is this optimal, right? What is this optimizing? So we kind of cheated by saying we want to maximize the likelihood, but now we introduce additional variables, these responsibility variables, we're actually maximizing both. What's happening there? So that will be our subject for next week. Is there any questions? Nope. I'm just going to stop the recording and wait a little bit. And in fact, I have my contact half an hour that's coming next. You can ask me anything.